stop talking. Okay, field trip schedule. This coming Saturday at 6 a.m. Leave Lubbock, TTU Jones Stadium West parking lot. Be on the bus, ready to go, no later than 5:45. We will have coffee and snack on the bus. Okay. 8:30, arrive at Highborn and have fun for a while. 11:30, leave Highborn, go to CSI. When we reach CSI, we will have Mr. Pula, what is the lunch over there? What do you have? Pizza or what?
They're Jason's Deli box lunches.
Jason Deli boxes. And we have veggie option, right? Vegetarian option.
We'll have 3 or 4 options when we get there.
Okay. And then anyone requiring special dietary? I think we will have enough for you. 3 we leave and 5 we arrive. PPE required, safety glass, wear clothes, toe shoes, and long pants. Okay, no short. And have your jacket, it can be cold. If you have any problem, that's a phone number. Question. Who drive by yourself to that place? Or everyone go with the bus? Then what is our policy on that? We provide a map later on Thursday, or no one drive by themselves, or some of them can.
Yes, I've had one person ask to drive by himself. We prefer you ride the bus. But if you have to, if there's reasons that are extenuating and they're really good, solid reasons, talk to me after class. But we prefer you ride the bus, and you need to be there early. At 6 o'clock we leave. And then if we leave and you're not on the bus, you're taking your own vehicle or you're not.
Will you drive by yourself or you go with the bus for this Saturday trip?
I go with the bus.
With the bus, okay. On other class, there are 5 grad students drive by themselves to Midland to the field trip, but in that course, total number of students is like less than 10 people. When they drive, there was a dead deer on the road, and they go over it. They almost die or something. So this, go with the bus, okay? And for the missing with university skills, you only for field trip. The rest, if you don't have university skills, you don't allowed to submit the report, okay? And okay, today we are going to go through a little bit of homework, last year exam, and then we finish a separator and go more emotion. This coming Thursday, bring calculator. I announced that on the blackboard, right? Bring calculator. It is more likely than not that we will have quiz. We may not have quiz, but if we have quiz and you don't have calculator, that's the problem. Okay? It is likely that we have quiz on this coming Thursday. And the quiz content I will tell you in a bit. Homework. Who haven't finished it yet? How many of you? Hasn't finished it. Who finished it already? Okay. So to be fair, for those who finished it already, I never extend any deadline, and to be fair for the student on the last year, I don't extend the deadline. Okay. I'm well aware that tomorrow is a job fair, and you'll be ready for that. Okay. And if you have interview, bring me university excuse letter. You can excuse from class, but you submit the report to substitute for that. Good? Okay. One of the homework that you may have problem. Okay, that's a homework 3. homework. Oh, let's go over exam. Last year exam. Last time is just I upload this. Who haven't downloaded yet? It is with the solution, and I able to find the solution for 2016. Everyone downloaded? Yes. And you can read it all you want. Okay. I'm not afraid of it. And the new exam should be new. But if it is the same, and it will be new, I will do it. I will do the new one. But if it's the same, you cannot say, hey, the student from this country, they have more benefit because they have the O exam. Everyone has the O exam. Alright? Plus the solution. And try to do it, okay, to prepare for the exam. There's true, false, question, and that's a thief. There's another vowel, separated question. Go through it, okay? And there are calculation question. I put 3 calculation question, and this one comes with a solution. If you have problem, you come to office hour of TA. You know the office hour time, right? Arya Shadi will sit in the TA room upstairs behind the main office. Okay? That's the O exam. New homework. New homework assigned today, we have just 6 questions. If you do at most 1 question, 1 hour per question, we have 6 questions, but you require to do just 5 to get 10. And at the end, what do? Remove 2 lowest score for homework and quiz, right? So try to start it early so that if you cannot do it, then you can go meet Arya Shadi on Wednesday. Okay, Wednesday is tomorrow, and this due next Tuesday. Okay, or you can meet me too if you cannot do it. Previous homework. Oh my God. Okay. Homework 2. I think question 1, everyone can do that. The one that may not quite clear is this one, this table, gas flow rate table. Okay. This table, when I do it, I get 13. Okay. For the case that I select earlier, I use 2-inch double X. You may use something else. Okay. The question here is, this table is for the case of 120 Fahrenheit, right? This is the gas velocity in mmSCFD, so that 13 mmSCFD will make the flow at 200 psi to be 80 feet per second. Okay, but if you have 80 F, this number won't remain the same. It will be something else. Okay, and if you use the formula given and you use table, you don't get the same number. I don't think you get the same number. Okay, and the value that you get from the formula is more accurate, but this one has some assumption in it. Okay, I want you to know that it's not the same. It's just not the same. So this is a gas throughput to provide 80 feet per second at 120 F. Okay, it's hot. Okay, and for the size of 2-inch double X, I can have 13. If the temperature is lower, Simon C. Achoku. Okay, if the temperature is lower, instead of 120, if it is like 60, what happened? Can I flow more than 13 million standard cubic foot per day in that part? Or I can just flow the same amount?
More than?
More or less?
More?
More. Why is that?
Because it said when the temperature is lower, right?
Okay. Temperature go down and then?
No, it's flow less.
Flow less?
No, because temperature is lower.
What did you say?
Because the temperature is low,
Okay.
then it's flow less,
So we can do more than 13 or less than 13?
less than that.
Less than 13. So if we have flow, so 13 will make 80 F per second at 120 Fahrenheit. If it is just 60 Fahrenheit, can it flow more in the pipe or it should flow less?
It should be more.
More than 13 or less than 13?
More than that.
Oh, okay, more than 13. When it is 60, gas shrink, right? Gas shrink. So when gas shrink, this means you can put more in the pipe so that it have the same velocity. So to achieve the same 80 feet per second, when gas shrink already, we should put more gas into it. Okay? It depends on how much it shrink. If it shrink by 100%, so that the volume decrease by half, then you can do 26, right? Good. Simon, you like 26? If it shrink by half or something? Yes. So if the gas shrink by half, the volume occupied the space is just half, then we can put more than 13 mmSCFD. mmSCFD, it is the volume flow rate at standard condition. It is equivalent to mass flow rate. Okay. It is not quite volume flow rate. It is, so basically one value of mmSCFD, we get one value of mass flow rate because it's a volume flow rate defined at the standard condition. Simon, you good with this? Have you done this question yet?
No, that's what I'm doing.
Oh, that's what you're doing, okay. Alright. Separator. We go over the internal part of the separator. We go through a big separator slug catcher, a little calculation on the Sonderbrau equation, and VT. Okay. So that's VT is terminal velocity calculation, and we go over this. And in the new homework, you see these two equations in the new homework. Oh, where's new homework? In the new homework, I think I asked you to derive something. So you will know it for sure because in the homework you asked to derive it of some of this constant. Okay, that is in the new homework. If you cannot do it, you may come see me. Alright, the part that we haven't done anything about is about sizing the separator. I already told you that the chart is available, and the reason that we don't use the chart is it's just 10% of the time that we don't use the chart. Okay, let's start the calculation. This slide about retention time and entrainment fraction, we go over it already. Demi something. What's your name? Demi what? Yes, you right hand. Yes.
Oh, me?
Yes.
Yeah,
Demi.
yeah.
What's the person next to you? What's his name?
Hamza.
What? Yeah, what's your name? Yeah.
Hamza. Hamza.
Hamza?
Yeah.
I will memorize the name. Hamza. What is the retention time?
30 seconds.
No, what is the definition of retention time? Wait a minute. What is the definition of retention time?
Average time of molecule or gas.
So everyone should know the retention time by now, right? So next one we will do the calculation of horizontal separator. And for more information, you buy this book. Okay, the calculation is in this book. But for now, I take part of this book and talk about it. Here's the formula for horizontal separator half full. Okay, the formula is given and we are going to derive it. D is the vessel internal diameter in inch, L effective length, T temperature in Röntgen, Q flow rate, mmSCFD, P operating pressure, PSIA, Z compressibility factor, D drag coefficient, D sub M, droplet size micron, and you can read all this, okay? If you put all this as in this unit, we get this equation, okay? You don't memorize the equation will be given. To use it, we will talk about it a little bit later, but now we will derive it first. Horizontal separator, we derive it based on the concept of retention time that Hamza just answered. Okay, retention time, we use velocity equal to volumetric flow rate divided by cross-section area. Okay. So VC is gas flow rate. If we think about the horizontal separator, okay, from the side view, we have it half full, gas flow on the top. Okay, when gas flow on the top, the cross-section area that gas can flow is top part, right? It's pi d squared over 4 multiplied by 0.5. That's the area for gas to flow. Flow rate, that is volumetric flow rate. Okay. Actual volumetric flow rate in the pipe. That is not standard cubic meter. That's not mmSCFD, not standard cubic feet per day. So that's the actual flow rate. And then we get the actual velocity in the pipe, or not in the pipe, in the horizontal separator that flow in top part. So we need to know how to, when we get this, then we know how fast that the molecule will travel horizontally. Okay, we will know how fast the molecule will travel horizontally. Okay, if we have quiz next time, of course you will need to know molecular structure of monoethylene glycol, right? MEG. You remember OH, line up, down, up, and then another OH. Got it? That's from the previous lecture. Review it. It is very likely to be on the quiz. And the next one is this equation, this part, these two lines. Okay, you will bring your calculator and you will show me how you get something like that. Not exactly like that, but so basically this Thursday I will know who don't know how to calculate, convert from standard cubic foot to actual cubic foot in the pipe. Capital Q without subscript G, that is actual volumetric flow rate. Okay, actual volumetric flow rate. This Q is standard cubic foot per day. Okay. Actual flow rate, that is in the unit of cubic foot per second. So I take mmSCFD, standard cubic foot, and do gas law PB equal to ZnRT. Okay. So basically, at the standard condition, gas already expand. When it is high pressure, at pressure P, and when it's a little hot, at temperature T, the gas is not as, doesn't occupy as large volume as when it is on the surface. So here's the equation. Ratio of the volume equal to ratio of ZT over P. Okay? So this is at the separator condition, and that is at the reference condition. Put it in, put R value in. Oh, you don't even need the R value. I think R value cancel each other. Okay? And do something that you will be quizzed on this coming Thursday. Maybe quizzed on this coming Thursday. So we will get this equation. Okay? The conversion from actual cubic foot and standard cubic foot. Right. Gas velocity, we have Q over A. Q over A. So Q is this equation, right? A is area, but this time we do just half of the separator. If we do full separator, it's pi d squared over 4, is that one. But if we do half, we multiply by 0.5. So area in the unit of inch, so that small d is inch, that capital D is feet in the unit of inch is d squared over 144. And basically we get that one. We put that one in over here, substitute everything in this equation, then we get Vg equal to 120 multiplied by something. Have you seen something like this before? Hamza, right? Have you seen something like this before?
Yeah.
When it is a flow in a pipe, it is not 120, it was what value? 60? Is it 60? Hamza? Yeah?
Sounds right.
That sounds right. You may recall when it is a flow in a pipe, what's that? I did not print it. When it is a flow in a pipe, when you are asked to calculate the actual velocity of flow in the pipe, the equation is almost the same except the coefficient. Previously it was 60, right? That one was 60, but this time I get 120. Okay, let's show you side by side. That one is 60. And this time I get, that's mine, 120. Okay, 120. Okay, this time I get 120 over there. Why is that? Why do I get 120? Aufstehen, Aufwärmen, Aufstehen.
Yes.
Why do I get 120 this time instead of 60? QG the same, right? That's QG and this QG. TZ and that's TZ. D square P, everything the same except the coefficient. Why this time it is 120 Aufstehen? You don't know? Who sits next to you? What's his name?
Ahmed.
Ahmed. Why is that? You don't know either. And next, what? What's your name again? Next to Ahmed?
Kareem.
Kareem. What is he looking at? Is that my slide?
Yeah.
Oh, okay, very good. So Kareem, why do you have 120? Why? Instead of 60, what happened? So all those three people get F or what? Who can help them? Yes, what's your name, sir?
Because velocity is Q over A, and A is 1/2.
A is just half, right? What's your name again?
Trent.
Trent.
Is that sound good?
Okay, name something, okay. I'll ask you later. So because the area is just half, so we have that. That's Vg. For horizontal separator, resident time of gas equal to the time required for droplet to fall. This time that for droplet to fall, if it is half full, it will be just half of the pipe diameter. So we have separator, we have half full, the droplet is on the top, the droplet fall, that distance is d over 2, right? Distance over velocity, we get the amount of time that it takes to fall down. We assume that it falls at terminal velocity, Vt. That's terminal velocity. And d over 2, if we change the unit from feet to diameter, is small d over 24. Okay? That's the unit conversion. That's equal to resident time, T sub d. Alright, that's the time required. Now think about it. When it fall down at L effective. Okay. L effective. And the velocity is Vg. That's the velocity when it fall down. Okay. Vg. Oh, this time, look at Vg. We go back and use that 120 thing. But if you notice, that Vg was the horizontal velocity, right? It was a horizontal velocity. So this side, L effective divided by Vg is horizontal length divided by horizontal velocity equal to the time that it takes to travel in the horizontal direction. Okay? This part is the time that it takes to travel in the horizontal direction. But this part, d over 2 over Vt. Vt is moving downward. Okay? d over 2 is the horizontal vertical distance. So on the right hand side, this part is the time required for it to move in the vertical direction. The time required for it to move in the horizontal direction and in the vertical direction, they're the same. Okay, equal to retention time. Okay, so that's why. So that's why I have this relationship. Good. Okay. TT settling time, I can take the first part. So it's L effective divided by horizontal length divided by horizontal velocity. That is settling time that I have. From terminal velocity equation, we have Vt equal to something over here. That is the force balance between the net buoyancy and the drag force. And in the homework, you are asked to divide that, okay? Which is just follow my slide and put the number on. So when we substitute everything, d over 24 Vt is that part, okay? L effective over Vg is this part, okay? Just put it in. Then we put Vt in, okay? Vt, okay, next, and the back, what's your name? Taylor, right? What's your last name? We have so.
Martin.
Martin. How do we get this? Where does that equation come from, Taylor? What is 0.0119 multiplied by bracket rho delta rho over rho g? What's that, Taylor? Terminal velocity. Okay, that's good. That's come from previous derivation. Okay, rearrange it, we get this equation, and this equation is the same as what I showed you early on. Done? Very good. So it's just a force balance. We basically make the time required to travel in the horizontal direction to be the same amount of time that is required to move downward. Okay. When you look at it, what is dm? dm. Trace, right? Trace, what is that dm? D sub m, what do you think? Is the diameter something? Diameter of what? Gas bubble, water droplet, oil droplet, or what is that dm? No. We have terminal velocity. Trace, what is that terminal velocity? It is the terminal velocity of liquid droplet in the gas medium, or what? What is that terminal velocity? Gas in liquid or liquid in gas? We are doing gas capacity calculation. So we have the separator on the side. We have droplet of liquid falling through gas medium. Okay, so that d sub m is the droplet size of the liquid droplet. Okay, and when we calculate c sub d, that's required what? Reynolds number, right? Rho Vd over mu. But that mu will be viscosity of the medium, which is gas. Viscosity of gas. Okay, that is for c sub d. Make sense? So this is for calculate the terminal velocity. Terminal velocity require CD or 24 over Reynolds number, and Reynolds number calculated based on the viscosity of the medium. Okay, you have this equation. I don't tell you how to use it. Let's do liquid capacity. Previously we do for the gas phase, right? For liquid phase, we just say, okay, just use retention time. Okay, retention time concept. With some derivation, I get that equation. L effective is horizontal length. Okay, TR, what's TR? Retention time. QL, liquid flow rate, barrel. Liquid flow rate, I think that's barrel per day. Did I put barrel per day? Yes, liquid flow rate, that's barrel per day. Okay, T, time in second, volume is, so to derive that equation, I get from retention time equal to volume divided by volumetric flow rate. Okay. In the lab, I didn't use the volume divided by volumetric flow rate. I calculate the average velocity first. After I get average velocity, I calculate the time required to move horizontally. But it is the same as that. Okay? So if we have volume, if it is half full, so when it is half full, it is that volume. So that's on the top. On the bottom, we have liquid part. So that is that volume of liquid part. Q is volume of liquid flow rate. So the time required for the liquid molecule to stay in the separator is volume of the liquid in the separator divided by the volumetric flow rate. Then we get T. Okay, and volume is I have half pi d square over 4 multiplied by length. Pi d square over 4 multiplied by length is that volume, the whole cylinder shape thing, right? And I multiply by half because it's half full. If it is 2/3 full, you put 2/3. Okay. If it is 75% full, put 0.75. If it is half full, put 1/2. Okay. Do some unit conversion and get that. Okay. Volume equal to some number multiplied by d square L effective. Then a little bit more unit conversion. Q. Okay. Q is flow rate in cubic feet per second. Previously we require flow rate in cubic feet per second for our derivation. Then we have after do some math, you should be able to do this too. So I have conversion factor and Q in the unit of barrel per day. Okay, because our formula needs barrel per day. But when we do derivation, we start from feet square per second. Okay, this is relationship between barrel per day and cubic feet per second. Put it in time equal to volume divided by flow rate. I get that equation 42 multiplied by something. Okay, and do some unit conversion, rearrange it, I get this equation. Okay. So this equation is for half full. If it is not half full, the number won't be 0.7, it will be something else, which you can tell me later in the exam if any, right? If it is 75% full. When do we do 75% full or like 80% full? Forrest R. Anderson. Where are you? Forrest R. Anderson. Forrest, where are you? When do we do very high level of liquid, like 80% full in a horizontal tank, horizontal separator? Have you seen it? Have you seen horizontal separator that have a lot of liquid inside? Simon, what are you doing? You haven't signed the sign up there?
The attendance was put over yet, so I'm trying to put the team in together.
Okay, you sign it, okay. So, Forrest, have you ever seen horizontal separator that have a lot of liquid inside? No? What about free water knockout? For free water knockout, do you expect the volume of liquid to be less than half or more than half? More. It's almost full, right? Free water knockout is almost full. Free water knockout will be like 80% full. It won't be half. Okay. Why do we need it to be very full for free water knockout? Who wants to answer it? Senior? Free water knockout, why should it be very full? Almost full, 80% full or something. Why is that? If I do like 10% full, is that okay? Not okay. Why? Free water knockout is to knock free water out. You want to separate water from oil, right? We have liquid phase, which is a mixture of water and oil. Free water knockout doesn't separate gas. We have to separate gas out first. So free water knockout operates at the very full, like this full, so that we have a lot of volume to do the separation. Make sense to you, senior? So if we do operate at just 10% full, we don't have enough, we don't have much volume. There's no point to buy a big separator. Okay? So we buy a big separator and we have to operate it correctly. For free water knockout, we do it more than half, almost full. So we have just small area for the gas. What happened to, so free water knockout, if I look at it from the side view, we have not much cross-section area for the gas phase, right? A little bit of gas phase. This means that gas will travel very fast, right? And we don't have much retention time for gas phase. But we have a lot of retention time for liquid phase. That's the key, okay? Based on this derivation, you will know that, hey, retention time is volume divided by flow rate. If volume is big, this free water knockout can accumulate larger volume, larger volumetric flow rate, right? Larger Q. So if we have more volume, VOL, we can have more volumetric flow rate coming in. If we operate free water knockout at 10%, so this means we don't have much volume for water to separate out. Then even though our separator is very big, the retention time is not much. Retention time is the actual volume occupied by liquid phase divided by the volumetric flow rate that's coming in. Okay? Isn't that why looking at the derivation make it very clear? Is it? Is it clearer? Yes? Yes. Okay. All right. Liquid capacity. We do something unit conversion to make it in the unit that we like. We get this equation. What about how do we select it? So we have one equation for liquid capacity, one equation for gas capacity. And next part that I would like to talk about is seam to seam length, L sub SS. Okay. You see the separator. This picture is come from Arnold's textbook. This one. So this part is curved. This part is curved, right? Seam to seam means just on the part that is not curved. That is the seam to seam length. What about the effective length, LEFF, that we talked about earlier? For the effective length in the gas part, it's just this length. Okay? Maybe that's too crowded. Effective length is just that. So that is the length for the droplet to fall, the length required for the droplet to separate. So if I have liquid droplet in a gas stream on the top part, it fall down, it move and it reach the liquid level. It requires L effective length. It requires that much length. Okay, that is L effective from gas capacity equation. For oil capacity equation, L effective is the length required to have that T sub R retention time, right? We have T sub R retention time and we have L effective. So with that L effective, if the separator is long enough, we can have that much retention time. Okay? So that L effective from liquid capacity and L effective from gas capacity, they're not the same when you calculate it. But when you look at the separator, there's one seam to seam length. Okay? We don't have the separator that look like this on the top and this on the bottom, right? It doesn't make sense, right? Okay. What do we do? You want to deal with this. First step, we need to know seam to seam. Seam to seam length can be calculated by two ways. This slide I updated a little bit. I put this word. If you print it out, you don't have this word. Okay. So L effective plus D over 12, that's for gas capacity. Okay, that's for gas capacity. Seam to seam length equal to 4 over 3 multiplied by L effective. That's for liquid capacity. Seam to seam length is in feet. Okay. So this means if I have L effective for the liquid from the liquid capacity part, I can have seam to seam length for the liquid part. If I have L effective from gas capacity equation, I have seam to seam length for the gas capacity part. Select whichever is larger. Got it? Select whichever is larger. Then we have to calculate the slenderness ratio. Okay. Slenderness ratio is the length of the diameter over diameter of the diameter of the cylinder. Slenderness ratio should be between 3 to 4. Equation for slenderness ratio is here. Okay, that's equation for slenderness ratio. LSS over D over 12. D is in inch, D over 12 is diameter in feet. Slenderness ratio is in feet. Everyone signed the sign-up sheet? Already? Yes? Where's the sign-up sheet? Where's the sign-up sheet? Okay. Who haven't come to class? How many? Tulani? Everyone come to class? Okay, very good. Okay, how do we use it? This equation is for half full. Step 1. Okay, look at this carefully. Step 1. We write down the retention time that we think we need. Okay. Maybe I have 3 minutes and 4 minutes. Okay. How do I know about retention? How much should be the retention time for liquid phase? I open the table and then I give the table. For the liquid phase, apical gravity of 30, retention time should be about 2 minutes. For 25, retention time should be 3 minutes. For 20 or less, retention time should be 4 or more. For very light gas, retention time for liquid phase, so this is liquid retention time guideline, right? Okay, so it can be half to 1 minute. If we have foam, multiply by 2. Okay? If we have carbon dioxide, use at least 5 minutes. That's a guideline. Okay, so when we do this sizing, we may have 3 minutes maybe enough, or maybe it is 4 minutes. It depends on what kind of oil, right? So if we know for sure that it is going to be apical gravity of 20, we may just use one number. But if we don't know, it may be apical gravity of 25 or maybe 20, so I have two numbers. It may be 3 or 4 minutes. So for each case, I can have diameter of several possible diameter. Okay, I may have 24, I may have 30, I may have 36. Okay, and for case or 42. For 4 minute retention time, I may have 24, 30, 36. For example, so the first column is retention time. Second column is the diameter. Okay. We list the cases, possible cases. We do the calculation and we select the one that it look good. Okay. So we list the possible retention time. It may be just one, and we list the possible size. They don't sell every size. We don't have 25.1, 2, 3, 4, right? They sell a certain size. Next step, for each diameter, calculate. So we put the diameter from, calculate effective length from the gas capacity equation. So we put diameter over here, temperature, compressibility factor, mmSF per day, pressure, operating pressure, density, CD, M, everything in, then we can calculate effective length. Okay, that is from gas capacity equation. Okay, back, next, oh, it's your turn. Last time is her. Okay, Basma, how do I get that CD, C sub D? Where do you get it from? It has to come from somewhere. You need help? Who do you want to help? Yes or no? 3, 2, 1. Okay, next student. 24 over Reynolds number. That's for laminar flow. For turbulent flow is 24 over Reynolds number plus something. Thank you, Basma. Okay, back of Basma. What's your name again? Steven. CD is 24 over Reynolds number. How do you get that Reynolds number? What is the equation for Reynolds number, first of all? What, Steven, wait. What is the equation for Reynolds number? No, I don't need the coefficient. You can remember. You can remember. Can I ask who do you want to help you? What's his name?
Daniel?
Daniel, do you remember Reynolds number equation?
No, I guarantee you I can Google this.
What's your name? Ryan, what is equation for Reynolds number? No need for coefficient. A. I cannot test you about Reynolds number equation. Okay, I just cannot. It's too easy. But memorize it. After this class, you should know raw video or meal. Memorize it. It's you don't have any formula to memorize. Okay, but that is one of them. Okay, Stephen and Daniel, you will memorize that. Raw video or meal. Okay, that meal will be meal of the medium. The medium is gas medium. So that is viscosity of gas. Then we open the fluid property book to calculate gas viscosity. Okay, and diameter will be the diameter of the droplet size that you want to remove to not plug the mist extractor. Everything about 100 micron and above, we should remove it. So that d sub m will be 100 micron. Okay. If we use just raw video or mil, everything has to be either SI unit or English unit, that everything cancel out. Otherwise, we need some kind of conversion factor. Okay. So that how we get L effective, okay, from gas capacity equation. Okay. For liquid part, I put retention time, flow rate divided by 0.7, I specify the D, I can get L effective. Okay? So I get L effective from both. And in each case, based on the L effective, I can calculate seam to seam length. Okay? I have seam to seam length. For gas equation, I use the top one, liquid, I use the bottom one. So I have seam to seam length. Then I select whichever is larger. Okay, seam to seam length. So this means for the case of 24 inches, I have seam to seam length equal to something. 30, I have seam to seam length equal to something. 36, I have seam to seam length, seam to seam length, seam to seam length. Of course, you have to do this in Excel. Then we calculate the slenderness ratio. We already know the diameter, so seam to seam length in feet divided by d over 12. So that gave us slenderness ratio. If we have several kind of ratio, select the one that is between 3 and 4. Done. Okay.